Okay, today I'm going to be doing this demo PC contest from February 2020. Um, yeah, I'm going to kind of just use this as a practice session, try to build good habits, think through problems clearly, write some nice code. Yeah, just have a good time. See what I can learn, what I see I need to improve, that sort of thing. Anyway, let's just get started right away. Okay. Did I submit to this? I did. Crap, I already did this contest. Whoops. So I guess we're not doing this one. Yeah, so let's do a different one then. Whoops. Which one was this? February? Lead contest? Participation. Yeah, I actually got the AK back in the day. Huh. Yeah, this was the weird one. Yeah, in the morning that I did it. Crap. Okay, so then I guess we do this thing. No, I also did this one. Okay. New Year's? No, this one. Maybe. Participation? I did it. Okay. Then okay, I know for sure I haven't done this one, so let's do this instead. Sorry about that. Okay, let's just get started. Problem A. I also might have to go grab some food in a little bit. But right now we've got 3 hours. Okay. Andy is traveling through the galaxy. His mission is to categorize the planets he passes. There are K types of planets he passes and different planets. Each of these planets can be classified as one of these K types. He would like to help Andy on his mission by programming a computer assistant. Whenever he passes a planet, he will tell the assistant the type of his planet. The assistant must tell him how many previous planets are of this type. Okay, this is just easy implementation with a map, I guess. Genie a.cpp. So what do? We read an end. Okay, this, should just work, right? Just implement what they say in the statement. Looks good. This one is a gimme. Am I stupid? Did I get it wrong? Whoops, I need to read in K as well. Now it's correct. So much for that. Didn't even pass the sample. I was a little too hasty. But so far so good. We get accepted. Let's move along. Predicting collisions. Let's do it. A bit of a longer statement, which is annoying. Willie lives let's also go to the contest page, I guess. Willie lives in a war zone and he's a Shoal soldier. Kolbeck Senior. Do I get penalized for that? Willie lives in a war zone. He's a soldier who wants to protect his planet. The planet's peacekeepers have gathered intel on the immediate missile launch that may affect his city. The missile launch is composed of 2 projectiles. There is a secret operation in Willie's planet. The operation involves extremely reactive substances that may destroy the planet if 2 projectiles collide within a specific area. He would like to find the collision point of the 2 projectiles' paths within the given boundaries. He's come to my help. For simplicity, the universe can be modeled as a 2D plane. The trajectory of each projectile can be modeled as a polynomial function. A collision is defined as a point where the 2 functions meet and are not tangent to each other, have to cross each other and not merely touch. The projectiles will not change course even if they collide because this is a new type of technology. Given the functions that represent the trajectories, find the collision point of the 2 projectiles within AB. In other words, find the value of this. There is only one point at this collision point. Input. Okay. Descending order. Got it. Okay, so let's consider let's consider the difference between them, and we want to find a 0. Cool, so let's just do it. Let's read it in. Okay, stop reading. Okay. Now we want to have an evaluate function. Now here's what we're going to do. Plus AI. I think it's this. Right? Yeah, this should work. Okay. Maybe we want these to be doubles, I guess. I'm not sure if they can be integers, but it doesn't really matter. If eval high is less than 0, swap AB, swap NM. Okay. Now I want to say this, and let's do it 100 times. We're going to do binary search. Cool. I think we also want to see out with fixed precision. So far, so good. Okay. Hopefully this gives 1. It does give 1. Let's just read over the code one more time. I read in the input, I evaluate my function. This is a minus b. At the right endpoint, we're going to say it's positive. At the next endpoint, it's negative. We want to find the point when they're equal, which is when it hits 0. So for this, we just use binary search. Code is short, code is clean. N plus 1 integers. Integers, A and B may not be integers, so I read them as a double. This should work. I see it with fixed precision. Okay. Weird. Huh. What's the set? M are up to this. Leading coefficient. These assertions are important. Maybe I want to see it with $15 digits of precision, I guess. Just to not care. Runtime error. Whoa. Oh, it may not even be correct. Yeah. Whoops. Whoopsie daisies. If we have something like that, then they're equal. Interesting. Yeah, binary search actually might not work. Maybe I just do Newton's method? Yeah, I just need to implement Newton's method. Okay. Mm-hmm. So I think I actually want to evaluate derivative. Okay, so okay. So this is going to be what's the formula? X is equal to x minus eval x over deriv x. If derivative of x, we need the absolute value of this to be greater than epsilon. then redo it. This. Okay. This works. If the derivative is 0, then we don't do anything and we say we've already found it 0. Okay, this was weird because I thought it was only like a continuous function, but the difference could have, wait, what? Why am I struggling with this? Just some random number? I think this Newton's method should work. I wonder if this is better. I don't know, something weird is going on here. This is Newton's method. This is weird. Yeah, I mean, it's just Newton's method. I wonder if we're going to pass the last test case. Still wrong answer? I wonder if this works. Yeah, we start with some initial point and we evaluate the derivative. Weird. What is going wrong here? I think this should be enough. Definitely we don't need all 0.8 seconds. This should be more than enough. Weird. Okay, what is going wrong here? Let's just think. This is kind of hard-coded. Maybe we put it here. This should also help us a bit. And we'll pick the midpoint to start with. So that we're always clamping it in. Okay, I also heard my phone buzz. Maybe my food is here. My food's almost here. Okay. So far so good. We're always clamping. Wrong answer. Maybe we should make this 1E9. I'm not sure, honestly. Something weird is happening. What is it? Evaluate the derivative. Could the derivative be 0? It could be 0. What if the derivative is 0? Maybe that's the last case. If the derivative is 0, it's guaranteed there's only one point in the domain where they meet and it's a collision point. Mm-hmm. I think this might work. Honestly, I'm not sure what's going on here. This is 1E9. Okay, let's try something interesting. We'll print the answer at the end. You want to find the thing that's closest to 0. No time sign, times over rand max. Okay. Okay, and then we do Newton's method otherwise. Cool. We try 100 random points. We want to find the one that's closest to 0. Newton's method shouldn't fail us on all of these. Okay, nice, we get accepted. That was tough. That was a tough problem. That was a tough problem. Yeah. It took me a while, but that was only because of this Newton's method thing. Okay. Let's keep it moving. I'm gonna grab some water and then we'll go from there. I guess the idea there was Newton's method, finding a 0 of a function. We need to choose some random seed to start from. You're going on vacation to your local group of exoplanets. In this group, there are n exoplanets lined up in a row. Each one is an ellipse consisting of a vertical radius hi and a horizontal radius that is infinitesimal. Okay. Okay, my food is here. We will take a break after I finish reading this. Grab the food. The ith exoplanet is Di from this. Okay? You plan to travel to each exoplanet starting with 1. On each one, you will stand at the very top of the exoplanet and look to the left towards this and to the right. You are curious about the largest exoplanet you can see in both directions. Next, you will continue to exoplanet 2, and so on. Got it. Cool. Okay. I understand this problem. I'm going to grab my dinner and then we will get to it. Okay, so I had a few seconds to think about this problem. And let's look at the fourth guy. The highest we could see on the right is this. So we're looking at basically the steepest thing. Time limit is very, very, very strict. Heights are this. Yeah. What does this problem remind me of? It reminds me of next greater element, right? We need to find the next greater element to the left and to the right of each number. The only thing is that we don't care about the next greater element, because for 2 here it would be 3. Wait, does it say we look up? Okay, so obviously we can see, what if everything is below us? It's not even necessary that we see everything. Which is interesting. Yeah. It's pretty interesting what's going on. Let me just eat this. I think the classic idea of the stack is important. The idea of the stack is important. Uh, It's also the distance between them. Okay. The distance between them is important. Yeah, we only care about some greedy subsequence starting here. Like we start from this thing, we go to the next grader, we go to the next grader. We need to say which one is it. Yeah, so we're thinking about the next greater thing to each side. That thing is obviously important, and we can compute that thing in linear time, which is a good start. Yeah. So let's think about the highest thing that this guy can see. It's going to be the highest slope. Yep. Let me also, I want to verify something. What happens if we're the tallest? I wonder what happens there. Let's go and draw a new grid. Let's say, let's fill it with black, no, fill it with 0. Okay. Let's say we're the tallest thing. Does it mean we can see everything? No, it doesn't, obviously, because for sure we can see this thing, but we can't see this thing because the one to the right is too small. And we're caring about the maximum height, right? So if we're the maximum, I claim we can see the maximum. Yeah, okay, so if we're the biggest thing, looking like in this direction, then we can for sure see the second biggest thing. Okay, so that case is easy. Yeah, that case is easy peasy. Okay, so we know how to handle the case when we're looking downwards. So now we need to handle the case when we're looking upwards. If we're looking upwards, I think the thing that matters is the thing that's the next greatest. So for 2, we would look at 3. And we would say, okay, what is the biggest thing that 3 can see? Biggest thing, and we break ties by leftness. So we say, okay, the biggest thing 3 can see is 6. But since the slope and the slope from 2 to 3 is, the slope from 2 to 3 is less than or equal to the slope from 3 to 6, then we say, okay, we can see what 3 can see. Else, the biggest thing we see is 3. And let's look at this case here. So this one for 1. For 1 can see 4. 4 is the next greater thing. The biggest thing 4 can see is 6. But since the distance from 4 to 6, sorry, since the slope from 4 to 6 is strictly less than the slope from 1 to 4, like if you were to draw these lines, we know we can't see 6. So I think just doing it greedy like this works. So we need to compute an x greater thing to the left and to the right. We need to compute prefix sums on distances to be able to query distances between I and j. Yeah, and then we need to have answer left, answer right. Yeah, I think should be good. Okay. Let's also get the fries. Oh, these fries are really bad. Okay, more fries after we get accepted here. Let's read an N. Whoops. Let's read the distances. It's going to be the distances between I and I plus 1. I think we want di plus equal di minus 1, because now we can easily query distances between I and j. Yeah. Let's do vector int big left, vector int big right, stack int stack. Okay. While the stack is not empty and h at I is greater than h at stack dot top dot pop. If size at stack big left I is equal to stack dot top stack dot push I. Okay, now we do the same thing for the right. I is n minus 1. What am I doing, bro? While the stack is not empty and h at I is greater than h at stack dot top stack dot pop. Okay, if size at stack big right I is equal to stack dot top. Push I. Yeah, because we're okay with equal elements. Yeah, we're okay with equal elements, so we make it strictly less. Okay, we calculated big left and big right. Now we also want the answer for left and for right. Okay. For int I 0, I less than n, I plus plus. If left I is greater than 0, cout h at left at I. And we'll print a space. If right is greater than 0, cout h at right at I. Else cout minus 1. New line. Oh, I could just do this in one line, you idiot. Left at I is greater than or equal to 0, h at left at I, else minus 1, Okay. Space, right at I is greater than or equal to 0. H at right of I, else minus 1. New line. Okay, nice one-line code to print the answer. H at left at I. Okay, fine. So far, so good. Now we just need to compute these arrays, and we've got the answer down. Okay, let's compute left first. I think I also might need integer 128. Actually, we'll see. I might need to use int 128, but we'll see. Okay. I think I also want prefix maximums and suffix maximums. And suffix at n. Let's compute these before we even start. Pre-I is equal to h at I, and these should be long logs. If I is greater than 0, pre-I is equal to maximum of itself, and pre-minus 1. For int I is n minus 1, I greater than 0, minus I. Cool. Suffix at I is equal to h at I. If I... No, I think we want strictly greater, right? We do want strictly greater. Yeah, we want strictly greater. Okay, if I plus 1 is less than n, suffix at I is equal to maximum of itself and its neighbor. Okay. So far, everything is O at n. So far, everything is O at n. Okay. This is me computing left. If big left at I is equal to minus 1, I think we want this to be pairs. Okay. Want these to be pairs. If it's minus 1, left at I is equal to pre of I minus 1 dot second. Else what? Should be fine. So we have something strictly greater than us. Big left at I. Okay. Now we need to compute the slope. So let's compute run is equal to d minus dj. Long rise is equal to hj minus hi. Cool. So this is going to be my run, my rise, long his. Okay. Because we know we can for sure see him, right? We're going to say left at I is equal to j. If left at j is greater than or equal to 0, cool. Then int k is equal to left at j. Long his run is equal to d at j minus d at k. Long his rise is equal to h at k d at j. No, h at j. Okay, this is his rise. Now we need Yeah, so we need my rise over my run. If it is strictly less than his rise over his run, take him. So we do need something else. Int 128 long. And we're gonna make these longs. Okay. If my rise times his run is less than or equal to his rise times my run, then left I is equal to k. Yeah, left at I is k. Cool. Now I just need to do the same thing from the other end. If big right I is equal to -1, right I is equal to suffix I plus 1 second, else what? Int j is equal to big right I, and my run is equal to what? It's going to equal d at j minus d at I. My rise is equal to h at j minus h at I. It's the same. Left j is left I is equal to j. If this should be right, my friend. Right j is greater than or equal to 0. Int k right j long his run is equal to dk minus dj. Yeah. His rise is equal to h at k minus h at j. If this is the same thing basically. Okay, and then we're gonna make this right instead. Okay, hopefully this is correct. I used the big integers when needed. Okay, it's fine. I want to do one extra test case. 3, 1, 2, 1, 1, 1, 1. Okay. So the highest thing this thing can see is 1 and 1 on both sides. Then we're good. Yeah, this is looking pretty good actually. Let's read through the code. Seems good. Everything is O at N. I don't think I use too much memory. Something here is weird. What am I doing that's wrong, man? Did this really just get wrong answer on the first case? That's really annoying. Oh. That's upsetting. Okay. Okay. Turns out, let me read the code and then we'll comment on this. Is this computing the distances correct? Yeah, I think it's correct. Yeah, I think it makes sense. This computation is correct. J's, J, this should be positive always. Where's K? Yeah, I'm not sure if this is correct. Maybe it's... So basically my idea looks something like let's, for each stick, find the next greater stick, and maybe it's the next greater stick there, but it can't be. No, maybe it could be. Maybe it could be, and now that we're just far enough away, we can see all the way over. Yeah, okay, so my idea was just wrong, and I just started coding way too early. Because now, whoops, we might be able to see. You think it's a bad drawing, but you see the point. It might not just be that. So there's a lot of things that could be wrong. Okay, so the slopes need to be strictly increasing. Wait, do they? Yeah, okay, let's think about it. Yep, the slopes need to be non-decreasing. Yep, and as long as that is the case, then we're good. Yeah, as long as the slopes between consecutive things are increasing, then we're good. Yeah, the slopes need to be increasing. And as long as the slopes are increasing, we can see the biggest thing. But let's say we see something smaller, we don't care about it. Yep. So we start here, we go to the next greater thing, we go to the next greater thing. Next greater thing as well. Wait, is this correct? That's kind of what I'm doing. No, because the slope here isn't increasing, but we could still see it because we're now far enough away. Because we're now far enough away, we can now see it again. I'm not so sure. Let's read this one. Queries. Okay. So you're curious, what is the maximum sum of the charges of particles from L to R inclusive if you look at exactly K? Wow, this problem's interesting. So obviously particles within the range we don't care about. Okay, let me draw something here. Okay, let's think about this problem for a bit. Say we have some things. So is n even? Not necessarily even, but I don't think it matters. Okay. If we have these things are paired, these things are paired, these things are paired. If the range includes both of them, like this, then we don't care about it. Okay, I'm not sure. I think I need to think about this problem a little more. I should be able to get this. It's kind of like next greater element, but not entirely. Like, we need the slopes from here to here to here to be increasing. So what does it mean? What do slopes mean? Slope is basically rise over run, right? So y1 minus y2 over x1 minus x2. Interesting. So let's maintain a stack of decreasing heights and while the slope from this to the top of the stack is less than the slope from this to this, then we pop. Yeah, that's got to be right. Because as we move, the x's are increasing, basically. And even here, anything that this guy can see, obviously this guy can see, anything that this guy can see, yeah. Okay, so we're just going to pop from the stack. I still need int 128s, but the stack is going to be of decreasing heights. Stack is going to be decreasing heights. Right. Okay. Now let's have a stack. Let's write this down so I don't forget it. Decreasing heights. Okay. This drawing is going to be my lifesaver. Whoa. Can I zoom out? I can. This drawing is going to be my lifesaver. Okay. So let's go for it. While I'm just going to make this a vector. While it's greater than or equal to 2. Mm-hmm. Okay, these are my things. What happens if we have something like this? Here's stick 1, here's stick 2, oops, here's stick 2, here's stick 3, then the slope is greater, so we would pop this thing. Yeah, I think it just works. Is equal to what? D at I minus D at A. H should be something like that. And we always take stack at 0. Yeah. Cool. If this, then we pop back, so rise A times run B. If this, else we break. Right. H at I is strictly greater than cool. Let's make sure that I get the lefts right. No, it's not just this. It's while yeah. Yeah, and you see eventually that that this thing comes back to life once we kill it off. Yeah. Thinks he's one. Yep. Cool. Now we can just run the same thing from the other side. Yeah. Whoops. Copy rise is D at A minus D at I. We could do it all in linear time with this stack. Okay. This should be right, my friend. Looks good. Looks good. Cool. Hopefully this gets accepted now. Ooh, baby. Talk about it. Talk about it. Yeah, it feels good. This was some geometry, really. But we're able to get it. Geometry was tough. But seeing this picture, what was it? This picture really helped me. Okay, now I have this. Exactly K particles. Then we have alien navigation. Number of ways. Okay. Let's read it. There are n. How much time do I have left, by the way? An hour, 30 minutes? Feeling good for 2 problems. I have read this one, I understand it. I don't have any ideas, so let's read this. There are n non-moving planets in the galaxy that can be represented as a 3D coordinate. Each planet is colonized by one of K alien colonies that exist. So recently the god of the galaxy decided to hold a meeting at the center of the galaxy. As a result, each colony must send one and only one alien representative to the meeting. But to get to the center of the galaxy, aliens must fly from one planet and move. Aliens must fly from a planet of their colony and move axis aligned and can only change directions at lattice points. Wait, what? Why is it 10? Oh, that's why it's 10. Okay. Interesting, because there's some lattice points. So if this was 2-dimensional, I know how to solve it. How many ways are there to go 3-dimensional? Wait, 3-dimensional binomial coefficients, basically. Something like that. How many ways are there to do it? I know how to do it with binomial coefficients. Yeah, so I basically need the function okay, the final problem. 2 ways are different if at least one of the paths taken by an alien is different, or if at least one alien is different from a different planet. So we can treat each colony separately. Yeah. And multiply them all together. And each of them, there's the shortest path, right? So this one, it only depends on the starting planet. Okay, this problem seems like it's more within grasp. Now I just need to figure out how many ways are there to do this. So we need ways A, B, C. Whoops. Which is the ways to go from 0, 0 to this by moving only up, left, down, or right. So we can basically say that there are, let's say n is equal to A plus B plus C. So there are n, choose C ways to do type 1 times n minus C, choose A ways. Yeah, this is the total number of ways. Okay? Okay? We're making progress. Yeah, and then we do the inclusion-exclusion trick. Yep, seems good to me. Yeah, okay. I'm gonna write it down, and then we use, yeah, so this idea doesn't slip. I'm gonna write it down. X. Don't forget it. Okay, here we go. Alien navigation. Genie, e.cpp. What else do I need? I need modint. Math modular. Okay, I'm gonna need my choose function. Okay, let's first initialize factorial with a million things. So far so good. Okay, let's just read the input. Cool. Let's do this as well. Cool. Let's have a comparator that does it by distance. Okay, and then we're going to do this. Who I with the comparator. Okay, we have the comparator now. Um, I'm gonna call this ID because I'm gonna use I later. Cool. Now, I think I need order. Interesting, because we can't touch things from other colonies, right? We're not allowed to touch things from other colonies. So how do we deal with that? I mean, we could just subtract it away from normal. Yeah, because we only care about starting here. Yeah. Yep. And I think I want this. Base on M1. Okay, and I also want order. Let's iota it. Iota this with 0, and then we'll sort it. Comparator. Am I doing something wrong? No. Okay. DPI is equal to ways. I'm going to call it paths. Oh. Obviously by the absolute value of coordinates. Okay. Okay, now this is what? DP is equal to paths from absolute value of x at ID, absolute value of y at ID, absolute value of z at ID. We have this. Now we loop over all j less than I if tj does not equal tid. And him is equal to order j if t at him is not equal t at me. I'm going to call it me. And at the end, we're going to say ways t at me times equal dp at me. Okay, so far so good. If this and distance from x at me, y at me, z at me, x at him, y at him, z at him is equal to the distance of x at me, y at me, z at me, 0, 0, 0, then dp me what do we do? What do we do? What do we do? What do we do with the dp at me? This is this J is the last thing that causes a problem. What does this mean? It means that cool. Yeah, it's dp type is equal to number paths to start that only hit guys that only hit this. So now we need to do does not equal type, I'm going to call it T. equal paths I think this works. Minus equal paths from me to him minus equal this. Yep. Should work. Let's check it. Ten. Oh no. So what's the sum of coordinates here? This thing is strictly greater than this thing. So let's do this. I should see this. Yeah. I don't see this. Whoops. Yeah. Yeah, it needs to be plus his distance. Okay, this should work. We pick the thing. We do this if it's blocking me. And we just have an n cubic dp. Okay, Mr. AQT. Weet wat? What? N equals 1. Which ones did I pass? N equals 1. Okay. Maybe if there's not one of each type, then we don't print it. Yeah, sorry, maybe this is the case? No? Each colony must send one and only one in the meeting. To get the center of the galaxy, aliens must fly from a certain planet of their colony. Oops. Am I just stupid, I think? Should be 0 at the beginning. We pick from 1 and then we multiply. Yes, we got it. Just some mathematics. Now we go to the last problem. Yeah, this was some mathematics. I had some stupid things with this Waze array, but yeah, wrote it in a nice cubic DP. Okay. An hour remaining, one problem. I can use a washroom and then let's solve this. Okay, let's think about it. Queries are answered online. So obviously, we need to consider the advantages of each element. What's an advantage? An advantage is the difference between the element and its like palindromic element. So this one, depending on which one is inside and which one is outside. So the ones that are completely inside, I mean, we can calculate this range. Completely inside, it's going to touch L or R. So then we have a new range. And basically everything in there, we get the sum for free. And then everything in here that we don't get, if this range is not empty, then we could spend any number of the k's on it. Yeah, let's just do a drawing. So, okay, what was my drawing? So, we're gonna have some range. I'll try and maybe I'll do like 6 elements or something, maybe 7. This is our entire range. There's going to be some prefix, let's call it a prefix, of things with the mirror element, like its neighbor, are inside the array. So maybe it looks something like this, and then these ones the neighbor is out over here somewhere. Okay. We will calculate the difference of this element. So it will be like x at basically n minus 1 minus I minus x at I. And we want to take the k biggest in this range. And that. The k biggest, if this range is not empty, like meaning that we have some of these, we can only take the ones that are basically greater than 0. Greater than or equal to 0. Else if this range is empty, then we're forced to take all of them except for basically k mod 2. Like if k mod 2 is this, then we're forced to take it, or else we could flip-floppy back and forth. So how do we handle these, like, more of Ninja Clasher's Wraith? If you look at exactly k. Yeah, so we need the k biggest of these differences. But these ranges are a little special. Starting here. Okay, k biggest. Yeah, we need the sum of the k biggest. Well, basically we can get max. I mean, do we want to do the ones that increase the sum by the most? Right? Right, so ba, 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 ba. Look at a particle more than once. Wait, k is fixed? K is fixed. Interesting. K is fixed. Interesting, K is fixed. Interesting. K is fixed. K is fixed. How do we use that? K is fixed. K, how do we use the fact K is fixed? How do I use the fact K is fixed? Maybe some square root decomposition. No. Obviously we take increases while we can. Then we just swap things around. So I think we can do some things offline, like we could rank them. Yeah, we can rank them. We could sort them. And then we try to take at most k of them. At most k of them. And then we want the sum of everything that is within LR, right? Do the increases offline. And I could do it kind of using binary search. How many of them are within LR? Then I could do the maximum. Or I skipped the last one. Okay. 45 minutes. Let's go, baby. I think I know how to solve this. Maximum 2e5. Okay, here we go. We're gonna need long N K Q, long A, C and N M, no N K Q for int I 0. Okay. Okay, now we need to have differences of left and differences of right. Pairs, right? What do we push back? We push back Okay, we're gonna sort the vec. We have n, which is the size, init. Okay. We have enough memory, which is good. query how many are there. Obviously, and we want to, this is going to be sorted. Vector, integers. We only care about the counts. I think it's only this. I think this is the data structure I want. I think this should be fast enough. Okay, we sort it. No, this isn't what I want. This is not the data structure I want. Yeah, I want it to be Gek Vita pushback. Okay. This, I finally think, is the data structure I want. Oopsie daisies. Okay, I feel like we finally have it. Okay, we have initialized it. Now we also need prefix sums. Cool. We built the prefix sum array. Now we just need to do a query, right? Can I do this query fast enough? Int cool, we read the input. Now what do we do? How much time? 30 minutes. Okay, we read the input, now we have two cases. Actually, let's read the input. Yeah, this is what I wanted to see. Oops, it should just be n, right? Don't need n anymore. Let's read what's going on here. Init is overflowing. Need to just return here. So far so good. Now we need to we can either say, okay, it's not in the middle. Then we just need to query LR. What is the new LMUR? If left is greater than right, Cool. I think this works so far. So we want to query answer plus your query 1. So what do? We either query some prefix with the same length, same query length as k, and we just take everything, same parity as k, or parity not equal to k. Yep. 1 is equal to query 1. 0 and this is with parity equal to k. Yep. I think we also want an infinity. Time check. Doing good. R. Mm-hmm. And I think we want GEC to actually plus equal the previous one, right? Plus equal the previous one. Okay, query 1 and query 2. These functions are going to be complicated to write. Is there something I could do that's easier? Wait, I think I just want query, right? I think I just want query. Yeah, I think I just want this to be a query function. And I want Boolean middle. I'm going to call this extra. I think we don't need half. cool. So let's think about it. Time check. 18 minutes. Okay, let's think. Let's think. So far, so good. Okay, what do we do? Come on, baby. Okay, these. How many are here? This is int. Okay. Man, this is getting complicated. Yeah, this is getting too complicated. I actually don't know if I can solve this in 15 minutes, so I'm just going to go for subtasks. So I'm just going to delete all this stuff. Maybe it's a cowardly play, but I don't know. I don't know if it is. Oh, I need this inside function. Yeah, just to get some more points. Right? Try and maximize my score. This is my middle. If it's middle. Okay, let's calculate the benefits we could get here. Okay, we have here. If it's inside, we take it. Okay, let's just run this. Cool. Hmm. If $10 now plus I think I can just do this, right? I can only take some positive amount of things. That's a bug. I mean, let's just go for it. Wrong answer? Okay, what is wrong with this? We sort it, we reverse it. Okay, let's try submitting this. Pretty focused. I did some good debugging. I think I fixed the bug here. Still wrong answer though. I think it's working. What's wrong here? Seems fine. Seems fine. Seems fine. I'm not sure what's wrong. It's both, and we print both. Is this the... Okay, so I think this case is finally working, but I don't have enough time to go for this because the contest ends in 40 seconds, but... So what do I know? This is working. This is working. This is suspicious. We can only take the same number of things as the things with the right parity, right? Let's just try resubmitting. How much time do I have? I could submit. So it ends at 14 seconds, but this is not going to be correct. Yeah, it's wrong. Inside floor of n over 2 and inside n minus 1 over 2. So for 4, this is going to give 2 and 1, which is correct. The distance to the left is this thing, the distance to the right is this thing. If it's the same, we print it, else one of them is bigger. So if left is greater than this, else this. I mean, it seems legit, but it's over. My participation scored 400 points. How good is that? Wait, what? 400 points puts me in 3rd place. Okay, I'm happy with that. I am happy with that. Yeah, and even Zihu Sang or whatever wasn't able to get this problem. Did anyone solve it? No. Wow. I'm surprised that I did that well. How does this guy do it in 7 minutes? Actually not sure. This problem, I guess, was my savior because I knew how to do it. Mm-hmm. Yeah, this problem was the one that I was able to see with inclusion-exclusion pretty simply. Yeah, because we say that the DP definition allows us to use inclusion-exclusion easily. Yep. Feels good, man, to get this correct. This DP definition is something I saw before on AtCoder. using this where we say this is the last thing that causes a problem. Yeah. And it works like that. Maybe I saw it in ICPC as well. But, yep. And then you just add the ways for each type and multiply them together. Yeah, that was this problem. Not so bad. Ninja Rat 2 feels bad to get this wrong. How many people, have actually solved this? Ninja Clasher and just a whole bunch of red people. Fine. I will try to upsolve it later. Data structures. Fine. Yeah. Let's go over some of the other problems quickly. My eyes. Which one was it? It was Golbeck Senior. Ninja Clasher's Wrath. This one was nice because it was geometry. Okay, so yeah, we'll go over problems here. Planet classification is a very easy implementation problem where you just maintain a hash map to store frequencies of each type. Easy peasy lemon squeezy. This one, predicting collisions, was not easy. I mean, was not as easy as it looks. This one, you're given two polynomials and you have to find a point where they cross. The input guarantees that there is exactly one position where this happens, and we need to find that point. Print it with very high precision. So my idea was you want to find where f at x equals g at x, right? This is equivalent to saying f at x minus g at x is equal to 0. So let's define h at x equal f at x minus g at x. And we want to find a 0 of h at x. And we know that there's exactly one 0. And we know that h at x is a polynomial. So this reminds me so much of my first year calculus class where we needed to use Newton's method to find zeros in engineering. And there's this formula that is an approximation, like iterative method to find zeros that basically uses the linear approximation of the tangent to the graph to compute like successive guesses for zeros, and then it converges pretty easily. The only problem is it doesn't always work. Sometimes Newton's method doesn't find a 0, which could be annoying. So how did I fix this in the code? Let's look at the problems. Where was it? This one. Predicting collisions. We needed to use Newton's method, but some initial seeds that you start with in Newton's method won't find a 0. So I fixed this the only way I know how, which is, this problem also took me a while, was by using random initial seeds, 100 random seeds, and then we pick the best. When we start an answer with 0, we seed the randomizer, we pick a random point in the interval, and then we just run Newton's method on it. Easy peasy, lemon squeezy. I wrote these functions for evaluating it and for the derivative. Cool. Ninja Clasher's Wrath is the last problem I'm going to go over because we already talked about problem 5 in the DP definition. This problem was actually tough. Was mine the best submission? It was. Wow, because it's completely linear. Did he use some segment trees or something? He's doing some convex hulls. Mine. Yeah, it's kind of like convex hulls. I mean, we talked about it a few hours ago. We need to maintain a stack from left to right, which has different pillars in decreasing orders of heights. And we basically need to say while the angle of this thing and this thing, while the angle of this thing to this thing is greater than or equal to the, like, while the hull looks like this, we basically remove this point. I mean, it's good that I learned convex hulls recently. It's basically the convex hull algorithm, because we know that this thing will never be used anymore. So how does it look? Pretty straightforward. We use int28s for computing the hull. And while the slope is greater than this slope, we remove it. And it's O(n), don't use any doubles, don't use anything like that. Completely fine. Yeah, basically we go through the stack and we say while this thing is worse, we remove it. Pretty tough. I didn't see that in my first submission actually to Ninja Clasher's Wrath. My first submission, I thought you only needed the first one, but then I saw a wrong answer. It was very annoying. Yeah. But eventually we were able to compute the hull, basically. I actually want to check one more thing. I want to remove this line of code. And see if we still get accepted. I don't think we will. I think removing more things at the end is bad. Yeah, that gives wrong answer. Nice. We definitely need to remove things from here, because we don't care about this thing anymore as soon as this is taller, right? We want the hull to be strictly decreasing heights as well. Yeah, this might have been my favorite problem of the contest. This might have been my favorite problem. Use some geometry that I recently learned, but in a non-intuitive way. Yeah. Yeah, I think that's it from me. This contest went pretty well. I'm surprised that I did so well. Maybe I'm actually improving a lot. Or maybe I just got lucky with the fourth problem, with problem E. Never know. I mean, it feels good to score 400 points with 355. Wait, that would have been, yeah, I would have been third place. Because they did ICPC scoring. Yeah, which is pretty nice. Definitely, this problem was my favorite. It took me an hour to think about it. And then this one was something I'd seen before-ish. There were some complications, like adding this extra dimension to the DP was not something I needed. I don't think I even need this who array anymore. Let's resubmit. Yeah, I don't need it. It should get accepted still. Yeah, it does. Best submissions, also me. Wow. Yeah, it feels good to get it. This problem wasn't really that complicated. I think I can also do it with 5. This should also be very fast. Yep, super duper fast. 3 times faster than the next fastest, basically. Feels good. It's good to see some rivals here that I want to beat. But yeah, I'm gonna end it here. Pretty good performance. This problem, I'm not sure about it. But yeah, I thought I had a brute force solution that worked for 10 to the 3, but it actually doesn't. So it's a bit upsetting. But for now, I'm gonna end it here.